entities, and I think again this is a lot of mumbo jumbo in this book. Really not that important. As you said, if you really see scenarios, I think as the examples go by, it will be a lot more clear. But basically, the ID dependent entities basically means that let's say there is a entity or a which is parts, and there is an entity called company. The company has the company name, city, country, and volume. Then there is a part name. When somebody is submitting a quotation, a part number is only valid within the company. So without the name of the company name, the part name is immaterial. So for something to be of any to identify a particular part number, even if part number is the primary key for this particular table or particular primary or the identifier for this particular entity, part number and company name together make a identifier, or they together the part number is ID dependent on the company. A part number without the company doesn't make any sense, because the part number is company dependent and part number is defined by the company. And that is the assumption in this particular example. You can have universal part numbers, but for this, we're saying that the part number is valid within the context of a company. So without company name, you cannot have a part number. So to design ID-dependent entities, you create the intersection table, and that's what he's talking about. This is the intersection table of quotation, which stores party number and company name, and the foreign key and the primary keys are in this table. So you create a table called quotation where you have company name, part name, and price. And so if you have a relationship like this, you create a table for part number, you create a table for company, and you create a table for quotation, which is the two primary keys, which are now together is the ID for this particular table. So if you have multi-valued dependencies, that a company, like in this example, in the data model, the company, city, volume, country, and volume, phone contact, company name, contact, and phone number. For this particular, there is a company can have 0 or many phones. A phone can be assigned to one and only one company. So if you see the way the diagram is done, what it basically tells us that a company can have 0 or many phones. A phone can belong to only one company. To convert that to a database design, we converted company name as a foreign key, contact as a key, and because the company name and the contact together makes the key for this relationship. So again, these are not very difficult concepts. The book has made it very difficult, but again, it is just trying to show you, if you had that kind of relationship, how you're going to create a table of this, a set of tables. So again, another example of a ID-dependent archetype relationship. A class has several sections. A class can have 0 or many sections. A section can belong to one and only one class. And if without a class, a section is irrelevant. A section has no value. So you must store the class name and section number together to make any sense out of. So that's the reason it's ID dependent, because it's dependent on the ID of the class name. So you can convert that to a class name, section number, class base, time, and professor into this particular database design. Okay, so we've done that. Again, the if you see what they're trying to say in this slide, is basically how do I take a set of data models and convert them to tables. And most of the time, the data models convert very well to the tables. Instead, if you have done the right data model, like the employee and the skill, if you have done two things, you took the employee, the employee has one or many skills, and for each skill, there is one or many employees. For any skill, there might be zero or many employees. An employee can have at least one skill or many skills. To normalize it, we converted those two entities into three entities, like we have talked about. So we took that, we converted it into three employees. Now we took the three entities and converted it into three tables. So if you've done your job, so these identifiers became primary keys, these are the primary keys, and here you tell each attribute, now you call it a column. Each column, what kind of value it can cause, all the data, what kind of data type it is, whether it is null, it's not null, what kind of constraints it has. So the idea behind everything that we're talking about in this particular class today is to take the entity relationship diagram and how to convert it to physical tables. And if we have done a good job with the entity relationship diagram, converting them to physical tables is relatively simple, as we are seeing there. So as you see right now. Okay, anybody who is not following what we're talking about? And again, we can go through tons of examples of how it is doing. The only way to get this correct is to take your data model that you have created, convert it into convert them into tables, and write SQL to create tables in SQL Server. That is the best way to clear everything up. I mean, you will probably understand this material in 30 minutes if you go sit in front of your SQL Server and start writing SQL to create tables. And you will see how, and SQL Server itself, the interface to create these things are extremely simple, and I think it will be very productive if you just keep this in the back of your mind, all the concepts that we're talking about. But once you have your database model and you have converted them to a database design, data model into a database design, you will be able to run them on a SQL Server, and you will learn all these concepts very, very, very quickly. Okay, so there's again the same thing. As a data model, we have a customer, we have sales order, we have salesperson, we have order line item, and the item. Again, the same concept the reason the project for this class is so important is anything that we are going to do in this, we are teaching in the class. That's your hands-on way of doing everything. And remember that in order to ensure good participation, I will ask each group member to evaluate other group members. That basically means that I will give 100 points. So if you have 4 members in the group, how you are going to divide it among those 4 members. So at the end of the project, I will ask each person to say how they are going to divide it up. And that gives me a good idea about participation and who put in, if somebody contributed more to the team. Usually people are, I see that in self-evaluation. If somebody is not putting their fair share of work into the project, I will know that because the other 3 persons will rate that person or assign them lower points. So make sure you put on your weight in the project so that you are not singled out by your teammates. It will be, everything will be confidential, so I am the only person who will see. So I'll ask each person to send me an email on how they're going to divide the points between their group members. Okay. So again, this is the data model. You have and you take the data model and you convert that to a database design. And the database design is basically very similar, just identifying the similarly on subtype, relationship, student, it can be a subtype. It's either an undergraduate student or a graduate student, so it's a yes or no. And again, this is the data model, this is the database design, and very, very, very similar. The Indian box cut thing we talked about today. This is the database design, and this is the data model. You see, the only thing that is extra here is box car number ahead. Because in the data, this is a logical design, you say there is at least 0 or 1 box car in front of me. Here you have to say what box car is in front of you. So either there will be a box car number or there will be nothing. So in order to do a physical thing, you can just say logically, I have a box car in front of me, I have a box car in front of me. You put in the box car that is in front of you, and you logically say, okay, I am the box car number X, number 5, and box car ahead of me is number 4. So then I have box car number 3, ahead of me is 2. I have box car number 11, ahead of me is 10. So that's what this basically says. So, and this is a clear example of that. You cannot just take exactly the ER diagram and convert it to exactly the same database design. You have to somehow think a little bit into it, because this is, especially on the recursive stuff, this is a logical design. It basically says there is a box car in front of me, 0 or 1 box car, but in a physical thing, you have to really say what box car is in front of me. And you have to store that relationship again and again and again. Because if you have 20 box cars, then you have 19 in front of you. So you have to say, I have 19, I have 18 in front of me, I have 17, so I think you got the point. Similarly, like the employee relationship we saw today, employee name and manager relationship, you have to have employee name manager currently. And who is the manager of this employee? So you have to, when you store, you can just store that I have employee and the employee is managed by employee, then I have a recursive relationship. I'm storing what is the employee name of the manager. And it will be, again, it will be very clear when you try to store the data and you say, okay, I have an employee and I'm trying to figure out all the managers, employees and all the managers. How do I store that information of employee? Because an employee can have a manager can have multiple employees, and an employee can report to only one manager. That means I have to store the employee manager's name for each employee. Same concept. Okay. I don't think. All right, I think we should go a little bit this must. A must constraint, a must not constraint, and must cover constraint requires that one entity must be combined with another entity in a ternary relationship. Okay, so let's look at this. Okay, so if there is a relationship that requires that one entity must be combined with another entity in a relationship, that basically means that for a salesperson, for a customer, if the customer number is 1010000, then the salesperson number is the first two character of the customer number. If it is 2000, then the first two characters of the sales, a salesperson number is nothing but first two character of the customer number, or first two number of the customer number. And is everybody still can see the screen? Okay, good. So I am not going to get into this. This is not a okay. Let's look at this. So relationship can have the following types of minimum cardinality: 0 to 0. I think we have already talked about this. 0 to optional to child optional, 0. Parent mandatory to child optional, 0 to M to M. We have already taken up this. We have already talked about all this. So I think that it's really okay. Cascading updates and deletes. Again, we think a cascading update occurs when a change to the parent's primary key is applied to child's foreign key. That means when the parent's primary key is updated, the child's foreign key is updated also, because they are related. A cascading delete occurs when associated with the child rows are deleted along with the deletion of the parent rows. So let's take an example, so that I think I'll give a couple of examples to say this. Let's say you have a department table and you have a employee table. In the department table, you have the name of all the departments. In the employee table, and then department and the name of the department, the head of the department, the contact phone number, all that kind of information. In the employee table, you have employee number, employee name, the department the employee works for, and all the other information related to the employee. Let's say the name of the department was IT, information technology, and they changed it to information technology services. Let's take an example. Okay, so they changed from IT to information technology services. So the cascading update occurs when you update the table in the parent, which is the department table, and the foreign key in the child is employee table, which is now also department in it. So you do update in such a way that if those tables, the cascading update occurs, that when somebody changes the name of the department from information technology to information technology services in the department table, it updates the child in a cascading manner. So all the department names in the employee table is also automatically updated. We have already got that. What is the cascading update is? Okay. The reason I ask all these is it's in a regular classroom. It's a lot easier to figure out when somebody is following you or not. Online it is almost impossible to know whether anybody is following you or not. So that's the reason I keep on asking, so that so that I know that you are following it. A cascading delete occurs when associated child rows are deleted along with the deletion of the parent row. So let's say you have a table where you are storing book information about books. In another table, you are storing in all the pages of the book. Okay? So, and information about each page. So if you delete the book without the pages makes no sense. So you delete all the books. Let's say a similar example. So let's say you have a apartment building with some apartments in it. So if you decide to demolish the apartment building and build something new there, then if you remove the apartment building, then all the apartments in that apartment building should also be deleted, because then there is no apartments without the apartment building. Doesn't make any sense. If you so those are the examples of cascading deletes. So a particular delete should cascade through the through the tables so that they are consistent. So the objective of cascading updates and cascading deletes is to make tables consistent, to make sure that there is no anomalies left when the update is created. Like when you do change the name of IT to information technology services, it is reflected in all the tables where there is a parent-child relationship. Similarly, if you are getting rid of apartment building, then the apartments itself doesn't make any sense, because the apartments only exist and they are weak entities. They exist in the context of apartment building. And so deleting apartment building means deleting apartments. So we should do that. So those are the examples of cascading and okay. Application programming uses SQL embedded in triggers, stored procedure, and other program code to accomplish a specific task. A trigger is a stored program that is executed by the DBMS whenever a specified event occurs on a specified table or view. Triggers are used to enforce minimum cardinality enforcement action not otherwise programmed into DBMS. So in this point, a trigger is a stored program that is executed by the DBMS whenever specified events occur. Like I said, if a department ceases to exist, then all employees to a particular department should be removed immediately. So it should be automatic. Like when we remove a department, like we said. So a cascading delete can be a delete can be implemented through a trigger. A trigger is a program that is executed when a specific event occurs. That means when we say we delete an apartment building, then delete all the apartments, or when we say we any kind of if there is we removed a book from the circulation, that means remove all the information about the pages. If you are maintaining a list of authors and a author you removed a book from the book list that we read, that means we also should remove the author that okay. Let's see. I think is that. Okay, so I think we've talked about the basic things that you need to know. Let's talk about this example. Beauty Gallery is a small art gallery that has been in business for 30 years. It sells contemporary European and North American fine art. View has one owner, 3 salespeople, and 2 workers. View owns all of the art itself. It holds no item on a consignment basis. So let's just think about this business problem. It is a small gallery. It sells contemporary European and North American art. Has one owner, 3 salespeople, and 2 workers. It owns all its art that it sells. It holds no items on a consignment basis. The application requirement: track customers and their artist interests, record gallery purchases, record customers' art purchases, list the artist and the work that has appeared in the gallery, report on how fast an artist's work has sold and at what margin, show current inventory in a web page. So this is the data model. So that's the problem that we had. I think, as you say, all the slides are online so you can see it. So this is the data model. So here is the customer. So we sold a customer. This is the customer number. And the customer admires 0 or many, has interest or is admired by, has interest in or admired by 0 or many artists. And then an artist is admired by 0 or many customers. Okay, the customer can admire more than 0 or many artists, or an artist is admired by 0 or more customers. That's what it is shown here. The customer purchases 0 or many things, transactions, 0 or many transactions. So the customer has 0 for each transaction. There is only 0 or 1 customer. Okay. I mean, this says 0 or 1, but I will argue that there is only 1, because how can you have a transaction to a 0 customer? But that's besides the point. It's just that's what the assumption is. So the customer requires 0 or more things, from paintings, and it is acquired. The word is title, copy, medium, or description, and created by. So this is the word that they acquired, the part of the transaction, and it is created by or created by the artist. Okay, so this is the word. Date acquired, acquisition price, date sold, sales price, asking price, and it acquired the work. This is the work that acquired, and it's created by this artist. So in the database design, we come in and we say, okay, here is a customer number, and all the information had interest in last name, first name, date acquired, title, and copy. Acquisition price. So this is the keys, and we'll say about that a little later. Let's say why it is. This is the customer. This is their primary key. This is the primary key, last name, first name of the artist. The work is identified by last name, first name, title, and copy. You can see why these are 4 primary keys. The transaction is required by the last name, first name, date acquired, title, copy. So this is the work, this is the transaction, and the only thing that is extra here is date acquired. Okay? And this work, this last name, first name is the artist. So this is how these 2 are related by last name and first name. These 4 are related by last name, first name, title, and copy. And date acquired is the unique identifier to identify the transaction. This is customer artist interest is last name, first name, and email. So this customer has interest in this artist. The artist is known by last name, first name. So if you can see that this here we went from this transaction, which was only in this was identified by date required in the model. It became these four things because we cannot really identify it. When you are doing a database from a logical to a physical, you must identify the transaction, and the transaction is identified by two things. One is who the artist is, last name, first name, what title of this artist we are talking about, and what copy of the title, because obviously we are not selling the real thing, we are selling copies of this particular artist, and this is the date acquired. So this is how we took from what we had is a data model to a database design. Okay, so then once we look at this, this is the first attempt at it, and then yeah, this probably will work. Now we look at it and say, okay, what are the changes that we need to make to this? Surrogate keys are needed for customer work and transaction. For all these, probably we can do it. Surrogate keys again, as we know earlier, is a system generated key, has no value for the end user, but has value for the system itself. So we can probably assign customer number to people, even if customer number doesn't mean a lot to the people or the customer themselves, to the work and to the transaction. We can use also a surrogate key for artists. This will change the identified relationship to non-identified relationship. Transfers customer ID null to allow acquisition without an immediate sell to a customer. So, okay, let's look at it what we did. So we, instead of having email as this address, we made customer ID, transaction ID, work ID, and artist ID, and these are really unique IDs that we have put it in here to identify work. And so with each work ID, we have a title, we have a copy, we have a medium, we have a description, we have an artist ID. Each transaction, we have a acquisition price. So again, the idea is you can do it this way if you wanted to. You can do it this way if you wanted to. So there is multi, again, in the database design, there is not one right or wrong answer, but there are multiple ways of doing the same thing. So so this is one way of doing it, that's another way of doing it. Okay. So I'm not going to, let me see what they, and again, they have come back and then they say how I'm going to do it. They're defining artist IDs, last name, first name, nationality, date of birth, and type, key, null status, and remark. And you can see, again, when you try to create this table in the SQL Server, you will see a lot of options like nationality in that allows you the range constraints that we're talking about, the value constraints, sorry, whatever the constraint, I'm forgetting. Hold on one second, let's go back there. What was that? Okay, I don't remember that. But anyway, the point is, let's go to that you can always specify that these are the valid values for nationality. So if you're anything other than Canadian, English, French, German, Mexican, Russian, and Spanish, or United States, it will not take. The system, the database will reject. Similarly, date of birth, you can say it's null and date of birth is less than date deceased. So date of birth has to be less than date deceased and has to be between 1900 and 2099. The date deceased has to be between. So these are the kind of remarks that you can put in the database itself. So again, the book has gone through this, and you can read it yourself. My only recommendation is that go in and even on this table, the view reads, go in and start creating it. You will understand this material more quickly if you try to if you start entering these into the database and start creating them. One second. And I will even, some of these, if you go in and start just recreating the view reads gallery database in the database itself in SQL Server, you will understand the concept of everything that we talked about today. So I will, if I were you, I will rather try to spend my time trying to go through the view reads database, create all the tables, take the database design, create all the tables, and that will give you everything that you need to know, rather than, this book is, I'm not discouraging you from reading the book, you can read through it, but that will make you learn everything a lot faster. Again, the basic design, the design 2 versus design 1, and design 1 is that the design 1 has bunch of keys. Again, it can be done. This is not, and it's assuming that one of the problem is that maybe not every customer is an email. I don't know whether that's valid. So there is some reason to do design 2, but design 1 is implementable in my opinion, and design 2 is also implementable. So you can decide whether you like design 1 or design 2. Both are their good and bad points, but that's not for me to decide. Okay, so I think, as I said, if you go in and start doing the view read gallery database in SQL Server, you will get all the concepts that we talked about in today's class very quickly, within an hour. And that's my thing. We will do chapter 5 and chapter 6 on the quiz next time. We'll go through chapter 7 and do the quiz. The quiz will be exactly the same that I did last time. It will be some multiple choice question, but it will be mostly short answer type. Let me see, I got feedback from 1 or 2 people, even the quiz was not enough time. How many of you think, we have now 19 people, how many of you think that the quiz, not the midterm, the quiz was not enough time, so that I can decide whether we need to increase the time? Okay, I have how many of you think we need more time for the same amount of material for the quiz? Last time I gave 35 minutes. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 10. Okay, so this time I will give 45. Again, my goal is for you to know the material. If you are looking through the book to find the answer, that's not what the goal is. So I'm not going to give so long a time that you can not come to the class and not know nothing and just searching through the material to find the answer. So that's not the goal. So I will give 45 minutes for similar amount of questions we had last time. And again, the goal is that you know the material before you come to the class, not search through the book to find what the answer is. Even if I were you, I will not even open the book because I should know what the answers are. Because if I'm flipping through the book to find the answer, I should not be able to find all the answers in the book by the time is up. So we'll do that. We will do 45 minutes. For the rest 20 minutes or so, you guys can do your project stuff. I'll keep the chat room open. And again, for the chapter 5 and 6. Okay, so if there are no other questions, I will hang up for today. You guys do your project thing, and next class we will finish chapter 7. Then we'll have the quiz. I think we'll probably do. I will try to finish by 9:15 or so. The actual database after the conceptual design, which is done today, there is nothing due. It's the last day of the class on August 1st when you do the presentation and you give me a copy of your project report. So last class, last day of the class, last day of okay. Yes, there is nothing else to turn in besides the conceptual design. Turn in the whole thing in the. That's correct. Okay. Good night, everybody.